This video shows a high-speed dash through a complex urban environment. The movement feels fluid, intuitive, and almost biological. But the computers driving these systems do not have eyes. They cannot perceive depth, recognize physical shapes, or judge real-world distances the way a human brain does. A microprocessor only understands numerical data. That creates an immediate, massive problem. How do you teach a blind machine to navigate a three-dimensional physical space? The answer relies on a mathematical framework developed nearly 400 years ago, a system explicitly designed to translate empty space into pure numbers. Look at this animation. When you strip away the textures, the lighting, and the physical rendering of a digital landscape, you are left with this, an abstract, strictly defined mathematical grid. This is coordinate geometry. It is the invisible blueprint that allows a machine to calculate, map, and interact with our physical universe. For centuries, algebra and geometry were isolated. Algebra was the language of equations, and geometry was the study of hand-drawn shapes. The two disciplines could not communicate. In the 17th century, mathematicians René Descartes and Pierre de Fermat sought a way to bridge that gap. They wanted to define physical shapes using nothing but algebraic equations. By laying down two perpendicular lines, an x-axis and a y-axis, they imposed a structured grid over an empty void. Suddenly, any specific location in infinite space could be assigned an exact numerical address, written as an ordered pair of coordinates. By assigning numbers to space, they permanently married geometry to algebra. A mathematician could now use an equation to draw a perfect circle without ever touching a compass. This new grid immediately solved a highly practical problem, calculating the exact distance between two locations in a void without needing a physical ruler to measure it. Mathematicians took the ancient Pythagorean theorem, where a squared plus b squared equals c squared, and applied it directly to the Cartesian plane. As you can see in this diagram, drawing a right triangle between two coordinate points allows you to measure the horizontal and vertical legs. By plugging those lengths into the equation, you find the exact length of the hypotenuse. We call that the distance formula. Today, it serves as the foundational mathematical engine behind trilateration and global positioning systems. This is the Magellan GPS 3000, an early piece of consumer hardware. Devices like this do not look at a map. They constantly crunch the distance between numerical satellite coordinates at the speed of light. Every time your smartphone routes your drive to work, it is rapidly solving that exact geometric distance formula millions of times a second. But navigation is only half the equation. If you want to make a video game character jump, how do you mathematically move a shape through space without redrawing it from scratch? The solution is a process called transformations. It allows you to change a shape's position, rotation, or size strictly by altering its underlying numerical coordinates. This animation illustrates the math in real time. By adding, multiplying, or swapping the x and y values of the polygon's vertices, you create translations, rotations, and dilations. Early computer graphics and CAD software relied entirely on this exact mathematics to manipulate geometric vertices and render 3D models. This principle applies directly to physical automation too. The precise movements of a robotic arm on an assembly line are dictated entirely by programmed coordinate transformations executed in three-dimensional space. Digital animation and automated robotics function through high-speed mathematical calculations that constantly update coordinate points. Before this invention, mathematicians were limited by what they could physically draft on a piece of paper. Once space was converted into a numerical grid, humanity gained the ability to define, model, and manipulate the entire universe using pure numbers. Mapping these shapes onto a grid allowed mathematicians to treat movement as a series of numerical changes. This ability to quantify motion provided the mechanics Isaac Newton used to develop calculus and the laws of physics. Today, that same framework is the engine powering orbital mechanics, software physics engines, and the autonomous navigation systems guiding drones through physical space. The next time you pull up a digital map, watch a 3D movie, or see a drone overhead, remember the math running beneath it. You are watching an invisible grid of numbers calculating physical reality.